So hello, everyone. My name is Matthew Rocklin. I work for Continuum Analytics, who's over there. We are we're a for-profit company inside of the open source Python ecosystem. So maintaining libraries like NumPy or Pandas, or we also produce things like Anaconda, or Bokeh, or Dask, or NumPy. Lots of fun open source software. I work on a library called Dask, which is a library for parallel computing. And so this is a little bit of a strange audience for me. I usually talk about distributed systems and numerical performance, and not so much about visualization. Out of curiosity, who in the room has heard of Dask? No, that's actually way higher than it was like even 6 months ago. So, okay, so what to expect? I'm going to talk a little bit about Dask, which is, again, a parallel computing library, nothing to do with visualization, you would think. However, it turns out that parallel and distributed computing are really hard unless you have really good information about your system. And nice, interactive, real-time visualizations are a great way to do that. So this is sort of an example talk. In particular, we're talking about sort of generally why visualizations are useful for parallel computing, and also in particular about Bokeh and Jupyter Lab, two things which Dask works well with, which we'll also hear talks of later on today. So it's a little bit of a example talk. Okay. Oops. Yeah. Okay. So again, I work on parallel algorithms and distributed computing. These things are hard. Everyone's sort of being dumped into this with the big data world, but we have relatively little expertise in this field as a community. Very few people were sort of taught from day one to think in a distributed way. We don't know how to debug well. We don't know how to reason well about communication. It's not something that our users have a lot of experience with. Fortunately, visualization can do a lot here to drive development, to tell us what needs to be worked on, and also to elevate the level of conversation. And we'll see good examples of that. So Dask is a library for parallel computing in Python. At a low level, it's a dynamic, low-latency task scheduler that thinks about data locality and resilience. If that makes sense to you, great. If not, don't worry about it. It lets you run Python code at scale. On top of this system, we've built things like parallel arrays, so parallel NumPy, parallel data frames, parallel Pandas, and also some Scikit-Learn things, and also just sort of general parallel computing. It originally was for a single machine, where things were sort of simpler. We've jumped out to clusters in the last sort of year-ish. And it's growing fairly rapidly. So one of the things that we did is we decided not to reinvent everything, and we are collaborating very strongly with NumPy developers, Pandas developers, Scikit-Learn developers, et cetera, which is why we've been able to move very quickly. So it was designed to complement the existing PyData space. Just out of curiosity, the audience, who here uses, say, Pandas? OK. Who here uses, say, R? It's the exact same hands. This is a great conference. OK. So quick example. What do we have here? Oh, that's not what I wanted to go. Things are. Let me realign my space a little bit here. OK, so a quick example. Is that visible in the back? Great. So I have some functions here that just sort of take a arbitrary amount of time and then return something small. So it's just a simple toy example. And I have some code that has some data. It runs those functions on that data, and then it does some sort of reduction on all those pieces of data. So this is just normal sequential Python code. It's going to take a little bit of time because we put some sleeps in that function. And it's running, and we're not quite sure when it's going to finish. Great, it finished. Took around 5 seconds. And so this is sort of the kind of code you might have that you might want to parallelize. So we're going to parallelize that with Dask, just sort of an example. And we're going to talk about sort of how we can visualize and get intuition off of those visuals. So the basic way to use Dask is to allow you to delay functions. This is sort of like how Luigi or Airflow or other sort of task schedulers might work, or Make, if you're familiar with Make. So I'm going to take those functions I just had. I'm going to wrap them in this function called delayed, which will tell them, OK, when I call you, don't actually run yet, but put some delayed computation in some graph somewhere that we're going to compute later. So as an example, I can compute increment of 1 and 2. I can add those two. And what that gives us is just a graph that we can evaluate later. So this is a pretty standard concept. People have seen this in lots of talks, I'm sort of hoping. We sort of delay computations, put them in a graph, and then later some other system, it could be a thread pool, it could be a cluster, can look at that graph and execute it in parallel. Okay. But it's very nice. This is our first visual. It's very nice to see this computation visually and see how it looks. This is just a simple graph viz plot. There's nothing fancy here. So then Dask can go ahead and compute that result and give us, here it was using threads on my local laptop, but it could have been using something else. So let's now rerun our original computation, but recalling that these functions, increment and double, are now these delayed versions. So now it's going to run immediately, because it just had to produce this graph. And instead, we get out this sort of computation that we can now evaluate in parallel in the future. So Dask allows you to write sort of arbitrary generic code as long as you're able to sort of pass all these delayed tokens through all these delayed functions with a nice result. So we can write generic code in a parallel way. And then again, we can compute that. And now instead of 5 seconds, it takes 2 seconds. Now, it wasn't perfectly parallelized, because this computation is not perfectly parallel. You can see there's some sequential dependence here. We can't run every task. We need to sort of wait until the dependencies finish. And we can see that here very, very easily from this visualization. Now, we might say, hey, we want to sort of avoid that, that kind of algorithm and do something a little more complex, like a tree reduction. So instead of adding all the elements one after the other, we might add pairs, and then add those pairs, and add those pairs in some sort of hierarchical tree. Because it's the same result, but it gives us a much more parallel-looking algorithm. So here we're able to experiment a little bit with different kinds of algorithms and see their differences and sort of really gain intuition about what's happening. And this is really hard. I want to sort of express to you how hard it is to gain intuition on parallel algorithms. Many people have these problems, and very few of them have experience in an academic setting, in even prior experience. Everyone's doing this sort of for the first time. And having these nice visuals is very pleasant. Okay. Another thing that sort of happens is that when we're running that computation, it's very nice to have visual feedback. So we're sort of running it, and it might take an hour, it might take a day, it might take 5 seconds, and we sort of want to know how long it's going to take. We want to get that, sort of reduce that anxiety. So this is the very first progress bar of Dask. Everything I'm talking about right now is Dask as of about 2 years ago. We have graph viz plots, and we have text progress bars. And if you saw me give a talk 2 years ago, this is what you saw. And so for the rest of the talk, we're going to see more and more neater things. But sort of the general gist I want to give away is that we care about intuition, building intuition, and we care about giving users real-time feedback so they understand what's happening. And giving them that understanding really helps them to react. It helps them to adapt to the system and work with it rather than sort of fight against it. It really changes the nature of the relationship. So on top of this sort of very generic system, we built things like parallel arrays and parallel data frames. As an example, I'm going to use Dask Array, which is a sort of sub-project of Dask, which implements a NumPy abstraction using many NumPy arrays. So here I've made a 15 by 15 array of ones, cut up into 5 by 5 NumPy arrays. So a 3 by 3 grid of 5 by 5 NumPy arrays. So this is sort of just a square arrays constructed of other square arrays, just using NumPy under the hood. So we see that there's 9 different boxes here. And what we can do is, as we sort of operate on this Dask array, we can see the algorithms that occur we can see how those algorithms look. And so here I'm summing along one axis. I might, let's say I will add x to its transpose. And so you can sort of think about how you expect this to look. Taking x, I'm sort of flipping it around, I'm adding it to itself. And you can see these sort of nice algorithms come out of it. Let's just go along for a little bit. So x dot dot. This is just to show the sort of complexity that arises pretty normally when using Dask. So people use Dask for all sorts of things. Dask arrays tend to be used for a lot of climate science. And they do these sorts of operations all the time. OK, so these are sort of the standard cryptographs that Dask produces. They become very complex, even with a very small amount of code. And Dask is very good at evaluating these sort of arbitrary task graphs very quickly. So for example, we can compute that, and Dask just ran through that in a small number of milliseconds. So it ran through all of those nodes in that graph. We're using many threads relatively quickly. And this is nice if you want to do sort of not a small array, but a larger array. You can compute on data sets that are larger than the RAM using all of your cores. Or again, on a cluster, all of the cores on the computer. So that's sort of where Dask was a couple of years ago. And since then, we've grown to do some more interesting things. So again, just very briefly, we saw that we can build intuition pretty quickly. Like people can sort of understand the differences between these two algorithms rapidly. I don't have to explain what tree reductions are. you sort of see this is a little bit more parallelizable than this one was, despite the fact that they are sort of semantically the same computation. So a couple weeks ago, I was sitting down with a colleague, Dan Allen, who works at Brookhaven National Lab nearby, and he has some large image processing pipeline coming off of a synchrotron, I think. And so we sat down and sort of learned Dask for an hour, then he rewrote his code in an hour, and we sort of ran some test data through it, got what seemed like the right result. We weren't totally confident, so we wanted to sort of first see and verify. And the thing that we did is we just visualized his computation on a very small data set. So normally, these computations are hundreds of thousands of nodes. You sort of can't visualize them, but on a very toy example, here's his pipeline. And he could easily point out, oh, yeah, this is where sort of this hierarchy is happening, and this is sort of this part is going away. It was very sort of intuitive for him to experience this. So just to give a non-toy example. OK, so visualization builds intuition. It also sort of pleases users with feedback. And these are two very different objectives. So on distributed systems, this gets more complex. We have data in different places. We have communication costs. We have workers with different abilities. Workers can go down. They can come up. The whole system is weirder. And we need to sort of convey all of that state to the user in an intuitive way. So things we might want to know, for example, is, OK, what's the resource usage on all of my machines and the memory usage? How is the communication, both sort of in aggregate, but also point to point? You know, is this node being hammered by all of the other nodes? So I want to see that if that occurs, because that tells me what to do, to how to react to that situation. I want to know all of my tasks when they finish, when they start, and when they finish on every different node. And if I have all that information, that really helps me to understand what my bottlenecks are, and so on and so on. And so this is the current Dask dashboard. This is built with Bokeh. And what you're seeing here on this side is every task that's running on the cluster. So I've got a very small cluster here. It's something like 15 cores. And over time, you're seeing what's occurring on that cluster, what's computing. So the x-axis is time, and the y-axis is the core that I'm using. You're seeing here we're running these green functions, and these sort of blue functions are coming afterwards. You can sort of double check down here to see what those are. I think Scott Sanderson gave a talk yesterday, sort of maybe was doing the same computation. Up on the left, we're seeing how saturated every worker is. So to the right of 0 is how many tasks we're running on any particular worker. And we want to sort of always see that that's always pretty much saturated. These workers have 4 cores, and you see that up until the end, they're pretty much saturated up here at 4. So they're always being well used. There's a backlog here of tasks on the left. That's the sort of bars that are going off to the left. So we see a nice little buffer on the workers as well. Seeing standard resource plots, standard worker things, progress bars, et cetera. So this was really valuable to have. When users now use Dask on a cluster, they have this. And it's incredibly valuable both to ease them and ease this anxiety, but also to give them intuition. OK, so to build that, that was a Bokeh server application. I'll talk a little bit about Bokeh. Disclaimer, I work for Continuum. Continuum pays me to work on Dask. Continuum also pays for Bokeh. So we're sort of like a tight family. But still, given that there was no other tool I saw that could allow me to build what we just saw in the amount of code that we just saw, that I am aware of. I would love to see counterexamples. So what we needed custom visualizations. We didn't just want scatter plots and plots. We wanted to build our own visuals because we sort of needed that control. We needed responsive real-time streaming. So Dask runs at about a millisecond overhead and about 10 milliseconds of latency. So we have a very tight loop, and we can use that to give users very rapid feedback, and that's of high value to us. So the example we just saw was on a small cluster, but we very often have hundreds of thousands of tasks we want to visualize all at once. So it's nice to be able to scale up to that if we need to. And additionally, I don't know JavaScript that well. And it's very hard to find distributed computing people, or people who know these sorts of algorithms, that also have a strong background in web programming. And so the fact that Bokeh runs in pure Python is very valuable. So what is Bokeh? Bokeh is a Python library for interactive visualizations on the web. You can use it for just sort of basic plots on a web page or in a notebook. You can also build it to build interactive streaming server applications. Some people call it sort of the shiny for Python. I go a little bit further, and it's the way to make streaming rich applications in Python with fairly simple code. So as an example, here is a periodic table with nice hover plots, hover tools, and this is a Bokeh visualization. This is a Bokeh plot. This is just a static plot in a web page. And how we can build that, I'm not going to zoom in here because the code is, I just want to show you the scale of code. This code is the code that's required to define the periodic table. This defines all of the elements. Okay. This code is the code to wrap visuals around that data. And this is all of it. And that gives us this. So this is sort of the nice, bespoke, custom visuals from a relatively moderate amount of Python, happily. Additionally, there's the Bokeh server. So imagine we had this plot, but we wanted to connect it to a spectrogram or something and have the different elements phase up and down based on the amount of the chemical we were seeing in a real-time feed of data, something like that. For that, you'd want something like Bokeh server, which does the same things. You have data sources. You then have plots that define visuals on those data sources. You can also update those visuals. So as a simple example, remember that sort of streaming plot of all the tasks that were happening? How I built that is that we have a column data source, which is sort of a table of data that has a few columns: the start time of every task, the end time of every task, what worker it occurred on, the way we want to color it, and sort of the name of the task. Was it an increment call? Was it an F? Was it a G? Et cetera. Then we define visuals around that, and this is sort of how that looks. We want to make a rectangle that starts at the start and stops at the stop, has a y-axis that is sort of the worker location. And then this is sort of the third piece that wasn't in the periodic table example. We then want to push data into that data source. So on my Dask centralized server, there's a loop that's just running, and it collects data from the scheduler. There's all this diagnostic data that we're collecting, and it just pushes that into this tasks data source. And Bokeh handles matching the state between the Python side and the JavaScript side. And that's really what, in my mind, that's what Bokeh server does. It maintains shared state between the web page that your users are using and a on-server side data frame-like object into which we can push data and also receive events. So there's also about 700 lines of Python. So the thing we just saw is about 700 lines. And it is one of the more sophisticated distributed computing dashboards I've seen. And it is very maintainable. So let's go on. My time limit is, organizers aren't there anymore. It's supposed to be off at like 10:25, is that accurate? 10:30, okay. That 5 minutes for questions or no? Okay. Excellent. Okay, cool. Okay, so let's look at this notebook. So as I said, Dask can do arbitrary task scheduling. It can also do things like big data frames and big arrays. So here's a larger data frame. So I've got 6 CSV files on HDFS on a small cluster. And what I want to read those in as sort of one logical Pandas data frame. So I can't fit all of that data in one computer, but I can break up that data into lots of little Pandas data frames strewn across my cluster. And then I can logically coordinate all of those Pandas data frames with one Dask data frame. So here I'm going to sort of load that data up, and these 6 CSV files become something like 91 little Pandas data frames, and we're seeing those load across a cluster. So here on the left, we have this function that's reading some block of bytes from HDFS, followed quickly by calling Pandas read CSV function. So we're complementing Pandas here. We're not replacing it. We're using it and complementing it with parallelism. And you see here, we have on the right, we have Jupyter or IPython widgets. On the left, we have this nice dashboard, and we can see what's happening over time. And the thing we get back is this Dask data frame, which looks just like a Pandas data frame. And it has all the sort of information we would find out of the New York City taxi cab data set. This is every taxi ride between January and June of 2015, including where they picked up. This is a common data set where they're dropped off, and sort of a breakdown of the fare, how much the tip was, how much the taxes and tolls were, et cetera. And so this implements a large fraction of the Pandas API. And you can see how it works. If we say compute something simple like the length, immediately on the left here, we saw that, OK, we computed the lengths of all the individual Pandas data frames. We then communicated all of those intermediate lengths to one node. It took around 22 milliseconds. And then we computed the sum of all those results. So this is how we compute the length of sort of many Pandas data frames to compute the logical length of one. And you can see, this all happened within, 50 or so milliseconds. It's sort of at human interactive timescales. Okay. A more complex example, we'll see how well New Yorkers tip by hour of day. So we're removing some rows that are sort of bad data. We're then making a new column, which is a tip fraction. So is it a 10% tip or 20% tip? And then we're grouping by hour of the day using nice Pandas datetime functionality, and then finding the average. And that was, a few thousand tasks you can see happening over here. If your cluster was well used, you can sort of break down what was happening over time. The result that we see is that New Yorkers tip pretty well, above 20% on average, and extraordinarily well at 4 a.m. It's 38% on average. My understanding is this is like last call at the bars. Yeah. Okay. So there we're seeing Dask run on a cluster, and everyone sort of understood what was happening over time because they probably weren't watching me on the right side, they're probably watching on the left side. They were watching the visuals because they look a lot prettier, and they give you information quickly, rapidly, in a stylistic way. Okay. So there's some benefits here. Users can sort of understand and optimize performance. If you give them information, they can react to it very well. It really reduces the load on the developer community because the users can handle a lot more things themselves. Additionally, the developers use this a lot. So a lot of those visuals I actually made when I started doing something. When we started making work stealing in Dask, I needed to know the load of every worker. And so I made one of those plots just to sort of drive my development experience. It was visualization-driven development. It also sort of increases the level of conversation. So often users would before say, okay, I'm trying to do something, it's slow. I say, I have no way how to help you, because I need to know so much more information. You know the size of your cluster, the speed of your interconnect, I need to know how your computation is built. There's just a lot of information that is very hard for them to deliver. The level of communication through text is sort of not sufficient. But now they send me plots like this. Say, hey, I'm trying to do this group aggregation with many groups. And it's being slow for some reason. Okay, great. I'm seeing two things are pointing out at me immediately. First, I'm seeing a lot of red, right? So red is communication time. And so, okay, you're moving a lot of communication between your nodes. Maybe you should think about how to serialize your data a little bit differently. Maybe you should think about, maybe you should be grouping by 100 million groups. You should try to reduce that a little bit. The other thing I'm seeing is on the right side of this, there's a lot of white space. That's space where the workers aren't active. There's only a few workers active at a time. So maybe our algorithms need to change a little bit in order to improve saturation. There's also some interesting things that are a little more nuanced, like these workers up here, they're looking a little bit qualitatively different from these workers down here. I'm sort of curious if his network has two different sides to it, or what's happening in that area. Things that you wouldn't easily be able to pick out except by sifting through logs. Another sort of general, I'll skip that for now. So that's Bokeh and that's Dask. I want to give sort of a shout out to Jupyter Lab for a moment. So I have a problem here, which is, so in this sort of GIF that I was presenting earlier, you notice that there's two different web pages that show different plots. And you didn't actually see this plot at all when I was working on the cluster. This side I didn't show, because I didn't have enough screen space. You'll notice also there's a little notebook sort of hidden here way in the corner, and very briefly on the left, there's a little terminal that I was using to capture the screencast. So I now have too many visuals that I cannot present all at the same time. And so for that, we've been using Jupyter Lab. So you can now put each of those individual plots inside of an interactive Jupyter Lab experience. So who here has heard of Jupyter Lab? Right, yeah, lots of people. Who here has actively used Jupyter Lab? Right, fewer people. I see the Jupyter Lab developer in the back raising his hand. Hi, Paul. Yeah, so Jupyter Lab is a way to bring all of your different things into one environment, and that helps a lot with organizing them. So this was built by, so there's a Dask Bokeh Jupyter Lab extension built by Luke Canavan in the span of about a week. I want to show it off for a little bit. So let's start a notebook. And let's also, so you'll notice that in Jupyter Lab now, if you install Dask-Lab extension, there's a nice Dask pane in Jupyter Lab. And we can add the task stream plot and the progress plot and the processing plot. So let's now shut that down, and we'll just construct our environment here for a moment. That one over here. Let's see. OK, great. So I'm connecting it down just to a little local cluster. I'm going to run a sort of a very similar computation from before. And we can now see that we can sort of play with these computations all in the same space. I can sort of move my plots around as I like. It's doing a little bit slowly, so I'm going to actually start up a new worker. So let's. This is a nice demonstration of both putting a terminal inside of Jupyter Lab and also that Dask can elastically scale out, which is convenient and pretty. And we're seeing that the workers are getting some use. We do a nice tree summation down here, sort of more fun computation, and we can now see all these things all at once. So allowing your environment to sort of integrate in this way is pleasant, especially when your environments become more complex, as they often do when you interact with clusters and dashboards and notebooks and terminals and everything, which is what you need when you do distributed computing. You need all of these things at once, and it's very awkward to have these different panes in these different worlds. So Jupyter Lab is a nice way to sort of bring them all together. Okay. What you just saw took Luke about a week to do, and it looks and it feels actually fairly first class. There's actually no substantive difference between the Dask Lab extension and the Jupyter Lab notebook. They're sort of both peers in the Jupyter Lab space. So it's very easy to enter, sort of not be second class to be first class in this world. So if you're building computational systems, I encourage you to try out Jupyter Lab. It's a great way to integrate into a larger experience. So screenshots in case you're looking at slides. These slides are online, by the way. If you look for my Twitter, it'll be there. So some final thoughts. So Dask provides parallelism for Python. So if you weren't here for the visualization conference or visualization, but you actually wanted to go to a parallel computing conference, lucky you should look at Dask, especially if you like sort of NumPy and Pandas and that sort of workflow. Additionally, visualization generally enhances computational systems. It's incredibly valuable. Dask became so much faster once we built the Bokeh dashboard, not because Bokeh made it faster, but because Bokeh made it super obvious where our performance problems were. And we just had that feedback, and that was incredibly valuable. It also gives users comfort, and it elevates the level of conversation. I want to sort of also point to, so we saw this nice Bokeh page. If you go to the Bokeh gallery, this is like one of dozens of beautiful plots. And there's probably something in whatever your field that looks like your field. I highly recommend the gallery. And then also for Bokeh server, if you go to demo.bokehplots.com, there's a sequence of small server applications that are running on a server you can play with and interact. So for example, here's a nice little thing you can play with is sort of the standard, sort of the standard drop-down change of plot sort of shiny example. So there's lots of fun things there. OK, if you want to hear other talks about Dask, I give lots of talks. Very rarely are they about visualization, but they're usually about different things. In SciPy, we talked generally about custom algorithms. At PyData DC a few months ago, we talked about fine-grained parallelism and sort of how the scheduler works. And here we're talking about visualization. And these slides are all tweeted under Rocklin. So my last name, Rocklin, them. OK, so that's it. If you want to go learn more, the Bokeh docs and the Jupyter Hub docs, the Dask docs are all there. And I'm open for questions. I think there's a gentleman walking around with a microphone.
So in the science world, we have a lot of legacy code, and I'm curious to know, will this work with executing like R or otherwise, or is there plans for that in the future?
Sorry, so you say will it work with R, or you say will it work with legacy code like Fortran code?
Yeah, we have code for algorithms written across every language you could imagine. If you probably you've never heard of. So.
Yeah. So I mean, so the abstraction of Dask is that it runs Python functions on Python objects. Python has a strong history with interacting with other languages. So if your Python function calls some Fortran code or some C code, that's totally fine. The Pandas example we saw does exactly that. It would be nice to integrate with something like R as well. So the task scheduler of Dask is language agnostic. That's about 90% of the cost. So if there's some bright R developer who understands the R networking stack, it'd actually be fairly feasible to hook in R clients and R workers into Dask as well. And that would be a nice collaboration. I'd be very open to that.
I have a question to the graph you're just displaying. The task graphs can get very complex, I guess. So have you explored Bokeh and its interactive features to explore the task graphs or animate them, like what we're just seeing?
Yeah, so this graph doesn't, so the graphs do get very complex, often hundreds of thousands or millions of nodes. This visualization that we're seeing here does not scale to hundreds of thousands or millions of nodes. Actually, a problem we're running into is this plot. So users don't use 10 cores or 20 cores. They use thousands of cores. And these plots start to break down. So something we're sort of thinking about now is how do we, Bokeh has no problem visualizing tens of thousands of elements on a page. It uses Canvas. But the plots stop having some meaning. And so we need to start thinking about visualizations that scale. And actually, I'd love for this community to think about, hey, how do we convey this information when there's not, here 150 lines, but 150,000 lines, or 1,000 lines, or 10,000 lines? How do we break down the information in different ways? I don't know much about visualization. I've gotten a lot of help from people like Sarah Bird, who's giving me a talk later on Bokeh, and from Luke Canavan, and you all probably know much more about this than I do.
Thank you, very nice. I'm glad you have this slide up. How are you choosing your color scales? And have you found that, in addition to the scaling problem you foresee or encountering, potential problems with the choice of the color scale, introducing artifacts in these kinds of visualizations? Have you done any work there, or how are you working along with that?
I think as we were growing, there were problems like we used to have borders around the boxes, and those borders ended up becoming the entire box. So remove the borders. There have been small things like that. I honestly don't know a whole lot about scaling visualizations that well. So I'm not qualified to answer your question. But you may be qualified, and I would love to chat with you afterwards.
Yeah. One quick question. So how do you handle multiple users running in the cluster? How do those visualizations will be affected by that? Yeah, so a question about multiple users. So we generally assume that all clients and all workers share the same software environment. So like your version of NumPy is the same as your friend's version of NumPy. But you can all use the same cluster. There's actually a nice deduplication. So you can both load the same data set, and if your friend has loaded it first, it'll just arrive. We use sort of a nice hashing, if you're familiar with Merkle DAGs. We're very strictly naming everything, so there's no collisions. Although when collisions occur, they're advantageous. There's first come, first serve scheduling. Most people who use this in a production environment tend to have every user have their own deployment of Dask, and they spin up and spin down, much like how a Spark job would work. But for more sort of institutional cases, you can have many users on the same set of workers, which has some benefits. Okay, I think we're out of time, so thank you all for your attention. I'll be sitting over there the whole day. Come on by.